Okay, so I will try to summarize what has been presented just before. So I apologize, I'm not at all an EFT expert, so I will try to do my best. But, I will need help. So here's a summary about EFT interpretation for the, let's say, the generic Higgs measurements. So at both experiments, we have interpretations for final states, for STXS combined measurement, and for Atlas, we have the Higgs STXS measurement, which has been combined with electroweak production boson measurements and even observables from LEP and SSC at the Z resonance. What we can say is that we have the same for a bit for CMS. So we have the interpretation for the electron final state for the STXS measurement, and also one measurement which targets for an interpretation in the TTH and TTZ boosted production modes. And what we can see is that the measurement get more and more sophisticated since we have a principal component analysis to identify the direction to which the analysis is sensitive to the combination of the Wilson coefficients. So if you prefer plots, this is how it looks like. Basically, here is a Atlas STXS combination. One can see the relative impact for the different STXS bins, and one can see clearly here to which coefficients you are getting sensitive. This is done mainly by scaling the parameter strings in each bin, and there is maybe no acceptance effects between different bins, which is taken into account. Here you have the STXS measurement for CMS, and you can see the interpretation in the Higgs effective Lagrangian model, and it looks here compatible with 0. And here the results for the Atlas STXS electroweak and precision observables combination. Here again, it's compatible with the standard model, except for this parameter, which, as Alexander was saying, is driven by the known forward backward asymmetries. And one can see as well that for most measurements, there is only one group of inputs which is driving the sensitivity, since you have only one component. Now, EFTs are very useful for the Higgs searches to search for non-resident production, so you can mimic additional non-standard model interactions with these operators. This is done with Heft operators, which are useful since they couple to the di-Higgs pair and up to single Higgs bosons. And here you have the results for CGTH and CTTH obtained by Atlas for the BB tau and UB gamma combination. And similarly, you have same kind of interpretation in CMS for the 4B final state and the multi-lepton final state. And here you have the exclusion limits for the CTTHH coupling in the kappa top frame. So regarding CP violation, what is new is that previously we had the limits obtained from the lepton final state. Now, considering this off-shell Higgs boson production, one can get an additional sensitivity, as it has been studied by CMS here. You can see the corresponding plot here. The production modes have been scrutinized as well in the VBF mode, and here we have a new result by Atlas in the H2 gamma gamma production mode. And what is used is matrix element techniques, which are combined in optimal observables. And here you have a nice constraint on this operator, which is interesting. And in CMS, it has been also done in VBS and GGH with 2 jets. But here in the Higgs tau final state, we assume that the Higgs tau is a standard model-like. use again matrix segment technique to get observables and also the azimuthal angle between two jets. And doing this, you can set a constraint on the coupling to gluons, combining it to other measurements, and you have we can exclude the CP out coupling at 2.4 sigma. So this was for the HVD couplings. Now, as we heard, there is a lot ongoing also to search for CP violation in the fermionic coupling and Yukawa coupling, trying to see if there is something on CP out contribution. So we have the two results by CMS and Atlas. The CMS result has been published recently. There is the pure CP out hypothesis is excluded at 3 sigma level. We have a similar exclusion done by Atlas, which has just been released. And the main difference between the two analyses is basically this categorization of the signal, of the Higgs signal in VDH and boosted categories, which we don't have in CMS. And finally, if one wants to compare with the results for the top quad coupling, so here again we exclude the pure CP out hypothesis at the level of 3.2 sigma and 3.9 sigma for both experiments, mainly looking at the TTH production, for lepton, gamma, gamma. And also, we just heard that there is a new result in Atlas using H2BB finite states, which are very challenging, but you can still have a first exclusion at 1.2 sigma. So, as a conclusion, everything looks standard model-like, but there is maybe still room to have a CP that's a mixture. We have only exclusion of the pure CP. So we can open the discussion now. I don't know. Maybe the speakers can join as well.
Yeah, I guess I would like to ask, are there projections of how much we can push down the composition of the CPO composition of the Higgs by the end of IUHC? Because looking at the pure CPO and saying something of the pure CPO when we are thinking that the Higgs are discovered regardless of the source doesn't make much sense to me.
No, so far I think it's just a benchmark.
No, I understand that you have to start somewhere, but that's why I'm asking, what are you thinking that would be your capabilities? I know that you always will do better than you expect, but still, what would be your capabilities hiding in the sea? So how much you expect to be able with this benchmark analysis push them to constrain something more recent, more interesting?
Andrea, I don't know if you have an answer. I don't have these data, right? Personally, I don't.
So for exactly the last slide, so we did in the Higgs et al. In CP measurement in Higgs et al. Couplings, so we did the prospects at HC, assuming basically just a scaling of the luminosity, and that was reaching 5 sigma. And an uncertainty on the angle of roughly 4 degrees. An uncertainty on the CP mixing angle of roughly 4 degrees, which at that point, in terms of remember correctly, expected it was 4 degrees at 60% confidence level. Okay, yeah, because here it's like 5 sigma 9, so it would be here.
You got 0 plus or minus 5 written. You have 0 plus or minus 5.
Plus or minus 5, yeah. Because, okay, plus or minus 4 was with the previous combination. Yeah. Plus or minus 5 degrees, which at that point could be interesting in terms of probing binary symmetry. So if I remember correctly, EDM model, the range would be around, if I remember correctly, 7 degrees in order to be in the range where you would have an effect that could explain binary symmetry. It was 7 degrees the CP contribution, if I remember correctly.
I don't know.
I'm going by the top of my head.
This is about correct. But it depends strongly on the method that is used to calculate it. There are two competing methods, and one gives you this number, and the other one gives you a symmetry about factor of 10 or even more smaller than.
Okay.
It's not really clarified in literature which.
But that is without, so what is which model are you thinking of? Because
It's no model, it's just assuming that the tau coupling is complex.
Yep.
Yeah.
and the tau effect is very small, no?
The tau is the best candidate in the standard model. With all the others, we are already quite restricted. From what we
But I
know,
don't
yeah.
understand the calculation.
I didn't do the calculation, I only know the result.
Which is the calculation?
There's a calculation that tells you if you assume in the early universe a complex Higgs coupling, that you can get a baryon symmetry, and depending on the method, an angle of about 7% can give you the right amount of baryon symmetry that you observe. Don't ask me how this has been done, I don't know.
Remove the deprivation.
I can tell you that. Look up my last paper on this, and there in the literature you find it.
I have, I can point to a paper exactly on that. I had it as well here, but then they told me refrain from putting lots about the interpretation, so I moved it. I had it here. I can point to the paper where the calculations are done.
For this extrapolation, how did you consider systematic uncertainties as well?
For this one, in this extrapolation, we kept conservative systematic interpretation to the one of Rankin.
Which one is the statistical improvement you get?
Exactly.
No,
So do you think this is?
So this is most likely, it's, I wouldn't say it's best case scenario, I would say it's more on the, just based on the sensitivity, as long as we can compensate with the increasing Fayard.
Did you allow for the physical constraints parameters in the extrapolation?
Yeah, talking right in front of you, I could understand nothing.
Sorry, we were discussing about other things.
Sorry, but you were talking about that, I couldn't hear anything from the
Related
back.
things, right?
So just one more quick question. Did you basically allow the fit in the extrapolation to constrain the nuisance parameters? Is there any chance that perhaps some of the nuisance parameters are constrained more than those others, so that it's not obvious it's a concern of it? Or did you just take, it depends how you did it, or did you instead, is it you scale everything up and you predict the fit, or it's just taking stuff and given uncertainties and imagining how this scale?
We did just luminosity scaling using combined harvester. So in terms of constraint on the systematics, I would need to look it up. From what I remember from the pools, we didn't have anything. So, okay, that was way, there's a problem in general with this analysis and pools. Since we are looking at a modulation, the pools are, okay, that I need to look at that. Okay.
Please go ahead then. No, please go ahead then.
Okay. It's non-trivial. The effect of any systematic on a modulation is non-trivial to quantify. So for that.
It should be realistic, but we don't know 100%.
Exactly.
Changing on topic of the EFTs. Something that I noticed that seems a bit like the single Higgs and double Higgs analysis in both experiments. I started one of sort of two parallel graphs, one left in single Higgs, half to double Higgs. But then in the double Higgs talks before, we were the next step when we want to combine single and double Higgs, and the interpretation should be somehow there to have some clear picture. I mean, the question is what should be the EFT framework to choose for this type of combination of single Higgs and double Higgs each. And prepare now, it's like on one side at least. Maybe it's more for the theories.
If I understand correctly, your question is like, I mean, in the using EFT, how we can combine the EFTs for the single Higgs and double Higgs?
Yes, but then the interpretation that now exists now of two different types, and then they're not going to combine.
The question is, what should we pick, right? Like, what should we publish?
Yes.
Which,
Because
yeah.
I think that if you just pick MEFT, in the only gain that you get from the Higgs is just the operator that modifies the state capture. You could even just import the modification, all the constraints from single Higgs and somehow plug them into the X. The result shouldn't be that different because the X is just the power constraint that operates. If you do this in EFT, you have a bit more global constraints because you don't rely more on the connection between GGH and GGH, for example, and maybe it's single X. And so there's pros and cons on both sides.
I mean, you would also, if you do a global interpretation of both, you would also have modification of the single Higgs couplings affecting the double Higgs self-coupling interaction.
Right, but this is not taking into account the curve, just kappa lambda phase degradation. Scale the range interaction of the water according to kappa lambda.
No, I'm speaking about the other ones that you fix to the standard model.
Yes. But then once we should pick something, one of the two. We should have had both cases.
And then on that question over there, I mean, as you were saying, HEFT is mostly relevant for double Higgs. For single Higgs, doesn't change much because you're probing Higgs coupling, single Higgs coupling to yellow particles. So it's not much HEFT can do there. So there's no sensitivity really to HEFT in single Higgs coupling. So if you want to combine, I think it's fine to do just SNAP because HEFT you probe just with double Higgs and that's it.
Is it something that if you think about going further, longer term, I don't know, including electroweak measurements or structural measurement, these things that can help make choice? I don't know if there's another advantage of not doing that.
I think HEFT is mostly decoupling the couplings of single, double, triple things.
Just for the Higgs sector or the other.
And that's the main point. So for single Higgs, very useful.
It seems to work for the Higgs plus electroweak field presented by Atlas, so why not continue?
And
HEFT has more parameters. More parameters. You couple things that are coupled in SNAP.
And I think there is also a chronological paper where some guys took the data from CMS as well as the Atlas publications for the electroweak results, Higgs, and other physics, and they just using the SNF to combine all the results. It is there. I have that link for that paper. So there's that they just took all of them and tried to combine all the physics results available using SNF. I mean, I think that's what you guys did. So it is just a separate couple of theories to try to just combine all the CMS Atlas data.
I mean, the advantage that you get by doing it in Atlas is that you can take care of some of the correlations, for example, that you don't have access to outside of the experiment, right?
Yeah.
So there's some advantage there, but yeah.
But what you said, that you can still, I mean, if you use math, you can combine those like outside the analysis. Of course, you still have the systematic alternatives that you can correlate. I mean, it's your
Yeah, right, but then the other.
I have another CP question if no one else has anything. So okay, we're setting limits on some CP odd contribution, right? And we can keep setting these limits because like you can always have some non-zero contribution. Now what I'm wondering is there like any particular value, now maybe like the 7% or whatever that were mentioned, any value that would be sort of like non-surprising where people would be like, I've been looking for this because the model that I like is exactly there. Because like the CP, fully CP odd maybe sort of like sticks out, but then like anything else, is there any point where we're sort of like, okay, now we excluded this set of parameters, this set of models, or is it just like, you just keep going?
The 7% are certainly a target, yeah? Although this is not a model that is assumed, it's just assuming complex Yukawas and then see what follows from it.
But this is like
And could you-
15. I'm looking at the paper.
Could you then like make up a model easily enough to?
This is a different question. And the models that I'm working in, the mixture is always much, much smaller. And you will not get there with the LHC. You will hardly get there with the plus-minus collider. Because all the other restrictions on the Higgs at 125 are already so strong. Yeah, but maybe you didn't think of the right model. Yeah, so this shouldn't stop you from measuring.
So I am looking at the paper. First, they never compute
Which paper?
the paper you're mentioning from Niosinir and Lina Foods and
Okay.
company. That is from March 2020. And well, I'm looking at it now, so I don't tell you much. But it's a dimension 6 operator analysis, and at least they don't say 7% anywhere in the abstract or the conclusions, that is the pieces I'm reading. They say, however, that they have to combine bottom, tau, and top, and the top and bottom bearing the new contribution. And I never see that they do a calculation of the strength of the electronic phase transition, and so. Well, I don't know. What do you mean, no, it's not even mentioned.
You assume that there is a
You assume. But how you assume, then you have to fit
No,
the physics.
the whole thing is, the whole thing is very political.
Yeah, that's the point. So to answer your
It's
question.
not wrong, but it's
No,
political.
but to answer your, I don't say it's wrong, and these are very good people, but I'm just saying that, I'm sure they thought about it carefully. But I'm just saying that it's certainly not a model, it's an effective in theory, and they are only looking at a piece of the puzzle, and you would have to build some theory to answer your question. It would be something that could test or prove or disprove. You cannot do it in this framework, because this is very hand-waving to do a piece of the puzzle.
So it's not an easy model to build. Like if we measure them, like today,
It's
I think we have like
effective
10 degrees plus minus 5. It's not like a trivial model to put up.
This is the usual thing with the EFTs, yeah? You may see some effect, which model does it fit? And if you find a very large effect, and I have my own question of this in a moment, yeah, I'm sure it will give people a very hard time, like it is with the flavor models.
So, okay, so my experimentalist view on this so far was that if we see something, like there will be all the papers coming out and like lots of choices, but okay, then perhaps I'm like too optimistic.
Try.
You can try us. Otherwise, you continue until the bitter.
But then, sorry, just to understand that 7%, the idea is you got the
7 degrees, but not 7%.
well,
Forget the
on the
same.
angles, can say.
7 degrees, I don't know where it is, it's not even in the abstract.
No, it's all crap.
With the current limits on the complex Fayard coupling, we can get something like 7 times the required variance.
That is all.
This says 0.
No, this is all crap. This is the case.
I'm reading the paper.
And we did this afterwards, and this is the number that we got out, together with Elina. Yeah? So we got, with the current limits on the Fayard coupling, something like 7 times the variance symmetry. So you can imagine you have less and you still get 1 out, which should be the target.
No, but there's 2 ways that this 7% can go. It can become folklore and then experimentalists go after this 7%, or it can be well justified and then we still go after the 7%.
It's an effective model, as also Marcella was saying. Yeah, it's not the concrete model behind it, just assuming that this coupling is right.
The contribution from like a complex coupling by itself is just a separate model. It's not even like basically just writing the Lagrangian with a CP odd contribution is just a model by itself. It's not it's not an effective field theory at all. It's a model.
maybe I can then ask my question I had in this direction. And for example, in the first talk I did on page 8, there was such a result.
First talk.
I know. I'm mistaken.
Can someone just send the video?
The talk by Alexander. That's this one, okay. Page 8. Page 6. One last slide. Yes! So, here you find values around 0, but for some of the operators you also find very large values. Anybody ever bothered to see whether there could be a model fitting these values? Or are they just so large that everybody thinks this is crazy and forget about it?
So I mean, the technical reason why they arise, I mean, there's some degeneracies.
Yeah, of course.
Question of
I mean, it's not a continuous range.
Yeah, I don't have the scans in the backup to see the bigger picture, but yeah. Now to the question of has anyone tried to fit a model to those? I don't know. And other people here might have a better.
That would be right outside.
Okay, then the question is, why are they looking at it? If you say, forget everything that goes beyond, I don't know, 5 here, yeah, then tell this to his random friends and they can make their life easier.
No, but I mean, experimentally, you can do the likelihood scan.
Yeah, of course you can do, but if somebody says, there the EFT is not applicable, okay, then you can do it, but it doesn't make any sense.
Right. So I think the difference is if you have some sort of bulk here that is still within that range, then perhaps there's some interest. Right? And then at some point then it's a political question, do you want to include this or not? Because still the reader of the paper can then make up their mind of what they want to do with the result. We just put the result out there.
I just want to understand, yeah, whether I wasn't aware that this is already outside the applicability.
Okay, I think this is the sort of the hot potato of validity that's pushed between experimental and theorists, right? The theorists say yes, linear is better, some say, but perhaps quadratic sometimes is nice.
Yeah.
Experimentalists do now both. So it's back to your side to decide which one you take, right? But I mean, it's obvious that these are quadratic terms create a set minimum at a value of 30. Quadratic terms might mean 900 times enhancement of the quadratic term.
Then you need the dimension 8 operators.
It just says that the quadratic term has an effect of 900 enhancement. What you think big of that is something different.
Okay.
And I think in this context there's also a different view, because the construction of effective components corresponds to the construction of the dimensional expansion at the level of the amplitude. And then observables are proportional to the square of the amplitude. So it means both of these options have their arguments. But of course, if you are seeing a sizable difference between including the square of the dimensions or greater, then of course it's a typical sign that your EFT might not be reliable.
I have a question on another topic about the combination of the Higgs measurements with the electrode measurements. I was wondering what are the gain, if any, in also combining with top work measurements.
Right, so I mean, certainly as you keep combining, you're going to be able to resolve some of these linear combinations that are down here, where we don't have sensitivity to now. And you're going to be able to then, you can pick, either you get more precision or you get more directions that you can measure simultaneously. I think the bigger question isn't so much sort of why is it not here? Well, no, the answer to the question is why is it not here yet? I think is not we don't want to do it. It's more technically it's not all that easy to have a consistent setup where you treat everything consistently with all the different input analyses, take care of potential overlap, take care of various other discrepancies that might be in the analyses, make sure that you scale everything that needs to be scaled, because then you need to think about potential effects also on the backgrounds in other analyses. So I think it's a technically difficult question, and I think the goal is very much to make that happen, because there will be additional gains possible. But yeah, it's not something that we're at the current stage. I think that's the politically correct statement to give. I don't know, like other people have plus one when I want to that.
Thank you.
Okay. I think
Just to add to this one, I mean, top of the background area. Once you add top as a measurement channel, the background to every other channel starts to change.
So you're saying it's difficult?
Yes.
The background to every single analysis changes, yeah.
Absolutely. Mm-hmm. I'm just translating.
We also get many operators because we can also see a lot of assumptions.
Can I just summarize to say that just one small comment is this you know, doing more work or something on this 7% number would be really important and impossible, I guess. But
yeah, I mean, of course, it's not impossible to do more work, but there are a lot of assumptions. For sure, for sure.
because
Sven can comment better.
it's just that
The main
this number is
problem
an
is, as I
example.
said, there are two different methods of the calculation, which disagree with each other strongly. Only the more favorable one gives you something that might be achievable in this kind of experiment. The other one gives you a far smaller diagonal symmetry, and forget about the LHC, and I don't know about the plus and minus.
Okay.
But the one method might be correct.
So, well, we take it with a pinch of salt. I think that's the bottom line. Thank you.
okay, thank you very much. I think we have to move to the next one.